Okay, so we're looking at graphing quadratic functions in vertex form. So, quadratic functions, okay, um, let's talk about that a little bit and see how it relates to what we've been doing. Um, you remember we've been dealing with quadratic equations. And so there's quadratic equations are a lot like quadratic functions, but the difference is that an equation is when the quadratic expression is set to equal something. And for example, we've set them equal to 0, so we can solve them using the quadratic formula. So, the quadratic equation is where the expression is set to equal a value, but a quadratic function has the quadratic expression just set to equal y, like this. Okay, and then when you plug in different values of x, you get a y that corresponds to each value of x. And then that makes a lot of ordered pairs, which you can then graph. So that's what we'll be talking about. Drawing that graph, which means showing all those ordered pairs that are generated when you put an x value, put something in for x. So that's the difference between an equation and a function. But we also have another thing that we notice is that this quadratic expression we have here doesn't really exactly look what we've been using. So let's look at that just to sort of see the differences and compare them and talk about what's going on. So we've been dealing with quadratic equations in standard form. And they look like this. And this is, whoops. Their standard form of a quadratic equation. So let's look at what a quadratic function in standard form looks like. So a quadratic function in standard form is going to look like this. Y equals ax squared plus bx plus c. So in the equations we've been working with, you set the expression to 0. A quadratic function in standard form would still be this standard form with something times x squared plus something times x plus a constant. But now it's a function, so when we put in a value for x, we get a y, and we get a bunch of ordered pairs that we could graph. So that is something we can compare with our quadratic function in vertex form. So you see the vertex form looks quite a bit different than the standard form, but notice they're both going to have x squared. The vertex form, you've got this x minus h binomial, and it's squared, right? So when that happens, you'll have x plus h. Just look at what that's going to look like. Right? X plus h times x plus h. And then there's a plus k. So we're not going to do it, but you would FOIL that, right? And when you did, you would get, x times x. There would be an x squared term. and there would be, this x times h gives us a middle term, and x times the other h gives us another middle term. So you would have something times x squared, and then you'd have something times x in the end. And then you'd have some numbers left over that aren't multiplied by anything. The h times the h, right? That does not have x. I mean, they're not multiplied by a variable. And then you'll have a k left over, which would combine with that. So I just thought, we should give a little context to these quadratic functions in vertex form to see that the vertex form is just another form for the quadratic. If you multiplied it out, like we're looking at here, you would have an x squared term and so on. And it is a quadratic. It's just written in another form. So why do we write them in this form? What's wrong with standard form? Well, nothing's wrong with standard form, but the vertex form is very convenient for graphing. We will learn, by the way, how to essentially put quadratics that are in standard form into vertex form. We'll look at how to find that vertex if they're initially in standard form. But that's for another day. So now we're just looking at the ones that are already in vertex form. And take a quick look at this. The graph will be a parabola, as you see this blue shape here. And the vertex will be h comma k. Whatever number h is the x-coordinate of the vertex, and whatever k is the y-coordinate of the vertex. Vertex being this small, the farthest down point in the graph. Now, parabolas can also be turned the other way so that they open downward, and then the vertex is that highest point. But this shows, what the coordinates of the vertex are hk, where the h comes from here and the k comes from there in the standard form. Now, a is also significant for the graph. Okay, that's the number out front. And if we did multiply this out, like we talked about and FOIL that, we would end up with a times x squared, just like you have something times x squared there, and we use the same letter a. So what is the significance of a for the graph? Well, we'll write a little summary here. H equals x coordinate of the vertex. K equals y coordinate of the vertex. And a, we call that, this is not a precise term. It's not really the slope, but we call it the slope of the quadratic. So it tells us something about the shape of that quadratic. And specifically, I have it labeled here, right here, okay? A will be how far up you go every time you go out 1 unit from that vertex. Okay, so if A is 4, for example, for every 1 unit you went out for the vertex, you would go up 4. It would be a really steep, it would be shaped more like this, because for every 1 that you go out, you go out 1, up 4 to get a point. Okay, if a is just a fraction, then it's very shallow and it doesn't go up very much at all. If a was, for example, something like 1/4 or 1/5, you would go up 1, but only, I'm sorry, go out 1 from the vertex, but you would only go up by a small number like a fourth or a fifth, whatever A is. So it would look some more like this in that case, very shallow. So when A is a fraction, something like that. Okay, if it's a small number. Okay, so that gives us an idea what A, X, and H are, how they affect the graph. And now we're just going to look at a couple of examples, and these are really, you can do them very quickly. So we just need to get the vertex and then look at A and decide how far up to go every time we go out from that vertex by just 1. So let's look at the first one. The vertex we'll identify here is, we said it's HK, right? H is just the number that's subtracted in the parentheses. You might remember this is very similar to what we did with the absolute value functions. They have a vertex, right? So H, recall, is the thing that's subtracted inside the parentheses. K is the thing that's added outside the parentheses. Just think of it that way. So here, 1 is the thing that's subtracted inside, right? So that's what H is, which is the X coordinate. It's just 1. Okay, then what is K? Oops, wrong eraser. I can't do that. I have to do it this way. Okay, 1 is the X coordinate, and then there it is, it's just 2. So we do not take the negative of the K when getting the Y coordinate, but we do take the negative of the number in here, in that what we use for the X coordinate of the vertex is the thing that's subtracted. So when it's a negative 1, we say what's subtracted in that case? Positive 1 is what's subtracted. So if you have a minus 1 inside, it will be positive 1. If you had a negative 1 inside, you would say, I'm sorry, if you have a negative 1 inside, it's positive 1. If you have a positive 1 inside, that's when it would be negative. And we will see one of those in a second. Okay, so we've got a vertex. 1 is subtracted, so the X coordinate is 1. 2 is added on the outside, so the Y coordinate is 2. So we'll plot that vertex right here. And then we look at the slope, what we call the slope A. And what is A in this one? What's multiplied out front? It's just 1, right? So when we go over 1, like that, we go up 1, and there we are. Oh, that's not very good. And when we go, my original point's not placed very well either. I'm a little bit of a stickler on getting this just right. Let's try again. 1, 2. Okay. So when we go over 1, we go up 1. No, we go, yeah, up 1. Because A is 1, right? So over 1, up 1 gets us right there. Over to the left, up 1 gets us right there. And now we've got these 3 points, and we just draw the parabola. Not very good at drawing parabolas. That's it. So let's look at the next one. I'll write down here A equals 1. So the next one, what's the vertex here? Oh, I left off one detail. Which way does this open? And we have it opening up, and that's correct. But we should write that down and make a note of it and make sure we get it right. It opens up because A is positive. Okay, there's nothing negative multiplied by this out front. It's positive, and that's why it opens up. Okay, so let's look at the next one. First we see, well, that's negative, so it's going to open downward. Okay. So let's find the vertex. The thing that's subtracted inside the parentheses, well, to write this as a subtraction, it would be minus a negative 3, right? So what's subtracted inside is negative 3. That's the x-coordinate. The y-coordinate is what's added out here, which is 1. So we've got our vertex, negative 3, 1. So these take a lot longer to describe and talk about. Since I'm trying to explain why it all works to some extent and explain it, it takes a lot longer to talk about than it does to just graph it. We have negative 3, 1 as our vertex, and then we have negative 1/3 is what we call that slope thing. So, and that's going to show us that it opens down as well, because when we go out by 1 from the vertex, we'll be going down by 1/3, right? A is negative 1/3. So go out 1, down by 1/3. So out 1 gets us to right there. Okay, I'll temporarily make that. That's out 1, right? And then from there we go down by 1/3, which is not very much, right? Like that. And we go the other side, out 1, we go down just 1/3. Something like that. And that's our parabola. Is shallow. It does eventually, try to make that a little more realistic. It does eventually get steeper and steeper. Something like that. Okay. So that's our two examples. That's it for today. We will be looking at them soon that are in standard form. Okay, they're a little bit harder to deal with, but that is graphing them when they're already in vertex form to make it easier for us. So that is all for now. See you later.